In the last section, we learned how to transform a matrix into row echelon form or reduced row echelon form using elementary row operations. So this process has a name. So let's define it. The process of using elementary row operations to transform a matrix to row echelon form is called Gaussian elimination. Now, if we continue on and further row reduce it to get to reduced row echelon form, then we call it Gauss-Jordan elimination. If we continue to transform the matrix to reduced row echelon form, the process is called Gauss-Jordan elimination. So we'll refer to this process using these names from now on. Now, there's some very important property about Gaussian elimination, Gauss-Jordan elimination. And that is, we can write an algorithm that tells us how to perform Gaussian elimination and how to perform Gauss-Jordan elimination. Okay? Now, an algorithm is just a set of instructions. Okay? At its most basic, it's just a set of instructions for how to do something. So a recipe on how to bake or cook something is a kind of algorithm. So let's take a look at this algorithm and let's apply it to an example. So let's take a simple matrix. 0, 1, 2, 2, 3, 4. And let's use Gaussian elimination. Let's use the Gaussian algorithm to row reduce this into row echelon form. Okay, so I'm going to very carefully follow this algorithm here. Right? So we're starting with a matrix. Let A be an m by n matrix. And we're going to set I equals to 1 initially. So just mentally, we have I equals 1. Okay? So if we have entirely zeros, we're done. Okay, we're already in row echelon form. That's not our case here. Okay? So otherwise, we want to find the first column from the left with a non-zero entry in row I or below row I. So in this case, row I is 1. So in row 1 or below row 1. Okay, so the first column with a non-zero entry in row 1 or below row 1, well, that would be column 1. Okay, I don't have a non-zero entry in row 1, but I do have a non-zero entry below row 1. Okay, so I'm going to be working in column 1. We're going to call this column the pivot column. So I'm going to go down the pivot column, beginning with row I, Again, I is 1, so beginning with row 1, and pick the topmost non-zero entry. And we're going to call it A. So I'm going to go down this first column, and I'm going to pick the first entry that's not 0. So it's not the first one, right? That is a 0. So we go down. Now that's not a 0, so that's the one we pick. Okay, so this is our A. If A is not in row I, so if this entry isn't in row I, which in our case is the first row, if it's not in the first row, switch rows so that A moves to row I. So that's my first elementary row operation I'm going to perform. I'm going to switch row 1 and row 2 so that I have a non-zero entry in row I, in my first row. So performing the elementary row operation, row 1 is 2, 2, row 2 is 0, 1, row 3 stays the same, 3, 4. Okay, so I've switched the rows. So now A is the leading entry in its row. So this entry, that's our A, it's the leading entry in its row. Okay. We're going to call this a pivot. Okay, so step 2 is done. Step 3. By subtracting multiples of the row containing A from rows below it, make each entry below A 0. Okay. So I'm going to subtract multiples of row 1 from the rows below it, so I make each entry below our pivot 0. Okay, so the goal is to make these 0. Now this is already 0, so I don't have to do anything there. But this one I do have to make 0. Okay, so I am going to subtract a multiple of this row from that row to make it 0. So let's do row 3, and then I'm going to subtract a multiple of row 1. And that's going to be my new row 3. So I'm going to leave row 1 the same. Row 2, I already have a 0 there, so I don't have to change it. But then if I do this elementary row operation, 3 minus 3 halves row 1. 3 halves times 2 is 3, so I get 3 minus 3 is 0. That's good. That's what I wanted. Okay. And then do the same thing for the next column. 4 minus 3 halves times 2. 3 halves times 2 is 3, so 4 minus 3 is 1. Okay. So I'm done with step 3. I've made each entry below A equal to 0. Each entry below this 2 is equal to 0. Beautiful. All right. Now, step 4. Set I equal to I plus 1. So right now I is 1. I'm going to make it 1 more. Okay. So it's no longer going to be 1. Now it's going to be 1 plus 1. It's going to be 2 next. I just increment it. Now, if I is bigger than m, bigger than the number of rows, then I stop. Okay, A is in row echelon form. So is 2 bigger than my number of rows? Well, no, I've got 3 rows. So I'm going to continue. Okay, and then I repeat steps 1 through 4 on the matrix, consisting of the remaining rows. When the process stops, we will be in row echelon form. So now I'm going to repeat it, but with I equals 2. So step 1. If A consists entirely of 0, stop. I don't have to stop there. Step 2, otherwise find the first column from the left containing a non-zero entry in row I or below row I. So now I is 2. So I want the first non-zero entry in row I or below row I, the first column with a non-zero entry. So I'm not going to use this column because all of these entries from row 2 down are 0. So going to column 2, I do have some entries that aren't 0 there, so I'm going to use column 2. Okay, that's going to be my pivot column for this round of the algorithm. That's my pivot column. Okay, so I'm working on it with column 2 here. Go down the pivot column beginning with row I. So this is row I. This is my pivot column. So I'm going to go down beginning with row I and pick the topmost non-zero entry. Well, the first entry, starting from row 2 going down, is row 2. I have a non-zero entry in column 2, row 2. So that's going to be my pivot. That is what I'm calling A. Okay. If A is not in row I, switch rows so that A moves to row I. I don't have to worry about that in this case. This entry is already in row 2. Okay. A is the leading entry in its row. Yes, it is. And so that's my pivot. So this is my pivot in column 2 for this round. Step 3. By subtracting multiples of the row containing A from rows below it, make each entry below A 0. So now I want every entry below this pivot to be 0. So I need to make this equal to 0. Okay, so to do that, I'm going to take row 3 and I'll just subtract 1 times row 1. And that'll be my new, 1 times row 2. And make that my new row 3. Okay, so I'm leaving row 1 the same. I'm leaving row 2 the same. In row 3, I'm going to take what was in my old row 3, 1, and subtract 1, and I get 0. Okay, and I need to do that for each element in the row, but if I do it for these zeros, obviously I just get 0, right? 0 minus 0 is 0. 1 minus 1 is 0. Okay? So I've completed step 3. Step 4, set I to I plus 1. So now I'm going to add 1 to I again. If I is greater than the number of rows, then stop. Well, I is equal to 3. It's not greater than the number of rows. It's equal to the number of rows. Okay? So let's repeat. Step 1. If A consists entirely of 0, stop. A is already in row echelon form. Otherwise, find the first column from the left containing a non-zero entry in row I or below row I. So if I look at row I, there is no non-zero entry in row I. There's no non-zero entry below row I. So I could skip step 2, which means I don't have to worry about step 3 either. Okay? I could go straight to step 4. I equals I plus 1. I equals 4, and now that's bigger than M, so now I stop. And this is in, this is in row echelon form. And it is. Right? We got that stair-step pattern. Okay? So this algorithm works. It actually gets us what we need. I would make one little correction. I would say I is greater than M, or if I is greater than n. Okay, if it's bigger than either one, I think the algorithm makes a little more sense with that. But other than that, the way it's written here is completely correct. And we get a matrix in row echelon form. Okay, I do want to emphasize that the algorithm isn't necessarily the only way to get a matrix in row echelon form. If I were doing this, what my first step would probably be, take this matrix and I'm like, oh, wait a second, this row has only 2's in it. I think I'm going to multiply row 2 by 1/2. So I get a row of 1's instead of a row of 2's. And that may make this row a little easier to work with. Okay, and then I'd continue from there. When I finish, I would get a different matrix in row echelon form. Okay, so what that means is that this algorithm, this Gaussian algorithm, it will always give us a matrix in row echelon form. But it's not the only way to get a matrix in row echelon form. If you do it, you might use an approach that's a little different than the algorithm and still get a matrix in row echelon form, and that's okay.